Dear students, I welcome you in this lecture on the topic projections of Hilbert spaces. Let us see the concept of projection on Hilbert spaces. Recall the definition of projection on a Banach space. A function p from B to B is called projection on Banach space B if P satisfies three conditions. First condition, P is linear. Second condition, P is bounded. And third condition, P is idempotent. Bounded and continuous happen to be the same for linear transformations. The context of this section is a Hilbert space H and not a Banach space. Recall that every Hilbert space is Banach space, but the converse is not true, that every Banach space is not a Hilbert space. Hence, H has an additional structure of inner product. This is because H has an additional structure of inner product. This gives many additional properties of Banach spaces over Hilbert spaces of projection. We will obtain and prove these properties in this topic. So, let us first see some basic properties. If P is projection on a linear space, if P is projection on linear space and L and M are range of P, then M can be described as Z set of all those vectors in L which are fixed by P. So Z dash belongs to L implies Pz dash and such that Pz dash is equal to Z dash. So Pz dash is equal to Z dash. M is set of those vectors in L which are fixed by P. Note that P is function on L. It is a projection on L, means it is a function of the type L to L which is linear, bounded and idempotent. Idempotent means P composition P equals to P. So this property is fairly simple. If Z dash belong to M, means we have PW is equal to W dash. So if Z dash belongs to M, there is Z belongs to L such that Pz is equal to Z, Z dash. Now using idempotent, we can easily get that P square Z equals to Pz dash, but Pz dash, so since P square Z equals to Pz, we have Pz equals to Pz dash, but Pz is nothing but Z dash. Hence, we have our required result that Z dash is equal to Pz dash. So, Z dash is fixed by P if Z dash belongs to the range M. M is nothing but set of all images of all vectors in set L. So, this property is fairly simple to prove. For converse, if Pz dash is equal to Z dash, then by definition of M, Z dash belongs to M. Thus, M is set of all those elements of H which are fixed by P. So recall that or remember that the range of projection on linear space is nothing but all those elements which are fixed by projection P, all those vectors which are fixed by P. Next property which we will study is this: let P be a projection on Hilbert space H with its range M and null space N. Then we have to prove that M is orthogonal to N if and only if P is equal to P star. So there will be two parts of the proof. P is equal to P star if and only if M is orthogonal to N. So if range and kernel are orthogonal to each other, then P is self-adjoint. So let us prove the first part. For proving first part, we consider, or the hypothesis in first part we take is M is orthogonal to N. And what we have to prove is this: P is equal to P star, that is P is self-adjoint. Since P is projection on H with its range M and N, we know that H is direct sum of M and N. We have proved this in the Banach spaces as well. Therefore, every vector Z in H can be written as x plus y, where x belongs to M and y belongs to N. X belongs to M and y belongs to N. So with this, take Z as x plus y, where x belongs to M and y belongs to N. Then consider the inner product of PZZ, that equals to inner product of PXY, x plus y. Since P is linear, this can be simplified as Px plus Py and x plus y. So further simplification is Px x plus y, because Py is 0 as y belongs to N. So due to this fact, it is P of x is 0. So it is nothing but inner product of x and x plus inner product of xy. But this is nothing but inner product of x and x, because inner product of x and y is 0 as x belongs to M and y belongs to N. Similarly, on computation of P star ZZ, inner product of P star ZZ, we get that it is equal to inner product of Z and PZ, which is nothing but x plus y, and inner product of Px plus y. So inner product of x plus y, Px plus Py, x plus y, Px. So it is x plus y and x, inner product of x plus y and x, and as seen before, this is nothing but inner product of x and x. So if we combine these two facts, which two facts? That inner product of PZZ equals to XX and inner product of P star Z also equals to x plus x, we get that these two are equal. Inner product of PZ equals to inner product of P star ZZ. Hence, we get the equality that PZZ equals to P star ZZ for every H Z belongs to H. By known theorem, which we have already proved in earlier sections, we must have P minus P star equals to 0, that is P equal to P star. So this completes the proof of first part. Now in second part, we are going to prove the converse. The converse is, if P is equal to P star, then M is orthogonal to N. That is, P is self-adjoint if and only if range and kernel are orthogonal to each other. So consider inner product of x and y. this is nothing equal to inner product of px0 and y as x belongs to M. So sorry, this is nothing but inner product of px and y because px is equal to x, since x belongs to M. We have px is equal to x. This implies that xy, inner product of x and y, equals to inner product of x and p star y. So thus, and since p is equal to p star, we can write this is equal to inner product of x and py. So we proved that inner product of x and y equals to inner product of x py. In next part, let us see the next part. Since we have inner product of, the next step is this equals to 0 because it is nothing but inner product of x and 0, since py is equal to 0 as y belongs to n. So thus what we proved? We proved that x is orthogonal to y because we obtained that inner product of x and y equals to x and 0 and that equals to 0 for x belongs to M and y belongs to n. This holds for every x belongs to M and y belongs to n. So we get that M is orthogonal to n. Third part. In third part, we are going to prove that if M is orthogonal to n, then P is equal to P star, then n is equal to M perpendicular. Note that M perpendicular is closed subset of Hilbert space H. Since closed subset of complete metric space is complete, M perpendicular is complete. So M perpendicular is a Banach space. As M is orthogonal to n, n is subset of M perpendicular, that is orthogonal complement of M perpendicular. Also, n is closed because orthogonal, because it is given, means it is a null space, so it is going always closed subset. So by known theorem, there is a vector z0 in M perpendicular such that z0 is orthogonal to n. We have proved this result in the topic orthogonal complements. You just recall this result and apply it here in this section. As M is orthogonal to n, we must have z0 in M. So thus z0 belongs to both of these sets, M as well as M perpendicular, but their intersection is singleton 0. So we must have z0 equal to 0. This is a contradiction. Therefore n is not equal to, therefore n must be equal to M perpendicular. Recall that we had assumed that n is not equal to M perpendicular. So our hypothesis was wrong, our assumption was wrong, hence we must have n equal to M perpendicular. So this completes the proof of this theorem. Thank you.